I'm Professor Rad, and this is Precalc video 1-1, Common Functions. One of the things that's going to be super important when you get into calculus is being able to move really fluidly between an algebraic expression and its graph. Sometimes features of the algebraic expression are going to inform what the graph is going to look like, and other times the graph is going to inform what the algebraic expression should look like. So you want to be able to see one and kind of have a little bit of familiarity with the other. So you know both algebraically and graphically what a cubic function ought to look like, or what an absolute value function should be looking like. So in this video, we're going to look at 11 common functions that form the foundation of those bigger, broader functions that we'll be looking at throughout the course of the semester and learning how to manipulate them. So for each of these functions, we're going to be talking about the name of the function, what is it called, how will we refer to it, the equation of the function, its domain and its range, and of course, what the graph is going to look like. So let's start out with probably one of the easiest functions, and this is the identity function. So the identity function has been given this name because it preserves the identity of the input. In other words, if I say, what's x? Your answer is x. What's 3? 3. So f of x is going to be x. It spits out exactly the same input. So the equation for the identity function is f of x equals x. The identity function forms the foundation for all linear functions. So if I take this function f of x and I manipulate it a little bit, maybe I shift it around, or I stretch it, or I reflect it, so I manipulate this basic function, I can get any linear function out of it. So that's what I mean when I say that these functions form the foundation. They're basically our basic building blocks for the functions that we'll be seeing in the future. Now, before I do the domain and the range, I like to do the graph next. Now you can create a table of values for this. This isn't super complicated, this function, so I'm just gonna go through it. So if x is 0, then y is the same as x, so y will be 0. So we go through the point 0, 0. If x is 1, y is 1. X and y are the same values for the identity function. So if x is 2, y is 2. And if x is 3, y is 3. Same thing with the negative numbers, right? So -1 is going to bring us to -1. -2 leads to -2. And -3 is going to take us to -3. So you can see we're getting a linear function out of this. So we'll connect the dots. To get our identity function. So to identify the domain of this function, we need to see what the possible x values are. I like to do this graphically for these functions. So I like to imagine when I find the domain graphically, I don't know why it's a giant metal sheet in my head, but it's a giant metal sheet, and it moves from left to right for the domain and from bottom to top for the range. So as I move from left to right for the domain, I want to see when does the sheet start hitting the function, and then when does it stop. Now, in this case, as I move from left to right, I have this arrow here pointing down and to the left, which means it's always going to be going to the left. So there is no like beginning point. It starts out at -infinity. So for our domain, we're going to begin at -infinity. Similarly, as we move to the right, we have this arrow that goes to the right forever. So that means we're never going to stop moving to the right. So we go off to +infinity. So the domain of this function is all real numbers. And that makes sense because you can give me any real number and I can spit any real number back at you. So this is using interval notation going from -infinity to infinity. If you prefer kind of a shortcut, the standard notation for real numbers is kind of this fancy looking R. So you might see this written as bold in text. This is referred to as blackboard bold. since I can't really write super bold differently from just my regular writing on the whiteboard. So I'm going to use this kind of double-edged here to indicate that the R is a bold. Or if you want to write it out in words, these are the real numbers. So you can use any of those expressions. You could use either interval notation, the bold R, or the words real numbers. The only caveat to that is if I ask for a specific notation. So if I say write your answer in interval notation, then it's going to have to write its words. It's going to have to be written as an interval. Okay, for the range, we'll do the same process, but we'll go from bottom to top. You never want to go from top down. That's your natural impulse because that's how we read. But when you find a domain or a range, you want to start with the negatives and move to the positives. So we're going to start at the bottom because that's where the negatives are and move to the top. Now, because we have an arrow that points down and to the left, but in this case down, and we have an arrow that points up forever, that means our range is going to be the same as our domain, which makes sense because this function takes a number and spits out the same number. So no matter what our inputs are, the outputs are going to be the same too. So the range of this function is also all real numbers, or if you prefer interval notation, negative infinity to infinity. So this is our first common function that we'll be looking at. I'm going to take a moment to erase the board and get us set up for the second common function in this video. Okay, through the power of TV magic, I erased the board quite quickly. If you want to pause here and set up a coordinate plane for your graphing, you can do that. We're going from about -2 up to 10 on the y-axis and from -4 to 4 on the x-axis. So this next function we're going to look at is called the squaring function. Now, one thing you're going to notice is that mathematicians aren't always the most clever when they name things. They're very straightforward. So the squaring function is going to take a value and square it. So the function equation says f of x is x squared, right? You give me a number like 7, and this function is going to square it and spit out 49. If you give me -2, it's going to spit out a +4. So as we did with the identity function, I'm going to go ahead and graph this one just by picking some nice numbers, plugging them in. So for instance, if I take 0 and I square 0, 0 times 0 is 0. Let's go with 1. 1 times 1 is 1. 2 squared is 4. And we'll do one more. 3 squared is 9. And we don't want to leave the negatives out. So -1 squared is +1. -2 squared is +4. And -3 squared is a +9. So when we plot these points, we're going to end up getting a parabola. Make sure your parabola is not pointy. Here, parabolas are nice and rounded. So I'm going to try and indicate that. Somewhat rounded here. There we go, a little bit better, a little bit. Okay, and for this one, I'm putting arrows on either end because I can give you any real number and you can square it. So if I gave you -pi, you could square it and get pi squared. So when I think about that and what it means in terms of the domain, I can give you any number and you can square it. So that means our domain is all real numbers. That makes sense graphically because we have arrows that point up, but importantly to the left and also up and to the right. So our domain is going to be all real numbers. The fancy R is my preferred way of just personally writing the real numbers, but again, you can use intervals or words, whatever suits you. For the range, this time we're going to have something a little bit different because as my metal sheet passes from the bottom to the top, notice there is nothing here on the negative side of this graph. So as it moves, it first hits the function at 0 when a y value is 0, And then as it moves through the top, these arrows continue to go upwards, so we have no ending at the top. So our range is going to start at 0 and go to infinity. Now, infinity is, in this case, a concept, so we're going to use an open bracket or parentheses. The 0 is included here because 0 squared was 0. So to indicate that the number 0 is included, I'm going to use a square bracket. So this would be our interval notation for the range of this function. Now we can also use what's sometimes called set builder notation to indicate the range. So I'm going to write that as well. Set builder notation starts out with a curly bracket or a brace. And it says the set of all, since we're doing range, let's use y. So that, and in this case, we have all y values that are greater than or equal to 0. So we have y is greater than or equal to 0. And then we close it up with a brace or curly bracket. So just a reminder, this vertical line means so that or such that. Before that line, you're just going to use the variable that you're using. So I could have used x. Honestly, I could use theta. I could use a smiley face, whatever you want to use. But whatever variable I choose to indicate here, I'm going to need to use in this expression. So if I had chosen to use an x here instead, just instead of a y, I would use an x here. So it doesn't matter. In this case, I chose to use y because this is the range, and the range are the y values. But again, in terms of the notation, it does not matter. Again, you can use whichever notation you feel more comfortable with, unless you're asked for a specific notation to use. So if I were to ask for interval notation, I would use this top notation. And if I wanted set builder, I would use this bottom notation here. Now, just like the identity function forms the foundation for all linear functions, the squaring function is going to form the foundation for all quadratics. So if I take this graph and I manipulate it, I stretch it, I shift it, I reflect it, I'm going to be able to get any parabolic function. I'm going to get any quadratic out of it. So that's what we'll be looking at towards the end of this first unit in more depth. We'll be looking at more features about quadratic functions. All right, let's move on to the third common function. Can you guess what it's going to be? All righty, did you guess the cubing function? So we have x squared, and now we can also have x cubed. So again, if you want to pause this video to copy down a graphing space, my vertical axis went from about -10 to 10. Oh, there goes my eraser, or up to 12 in this case. And my horizontal axis went from about -4 to 4. All right, so as I said, the cubing function is going to cube our value. So f of x will be x cubed. So as we've been doing, let's create the graph of this. So I'm going to start with 0 again. 0 cubed is 0 times 0 times 0, which is 0. 1 cubed is going to be 1. Now on the graph space that I've used here, notice that I've counted by 1s for each tick mark on the horizontal, but I've counted by 2s for the vertical axis. So you want to bear that in mind as you're graphing. So that means my 1 value on the x-axis is here, and 1 on the vertical axis is going to be between the 0 and the first tick mark. So we're about halfway there. 2 cubed is 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. 4 times 2 is 8. And 3 is going to be off the charts, because if I try to cube 3, 3 times 3 is 9, and 9 times 3 is 27. And I don't have enough graphing space to go up there. But I do know it's going to be increasing pretty quickly. Now, if we go on the negative side, -1 times -1 is 1, times -1 is a -1. So unlike with the squaring function, we're going to get negative values. -2 cubed is going to be -2 times -2, which is 4, times another -2. So 4 times -2 is -8. Do that here. And similarly, -3 cubed will bring us down to -27. So for this function, we're going to get increasing up here. It's going to be going down over on this side. And then in the middle, it does a little shimmy. So we're going to kind of start it out a little bit like a parabola. So it's going to be going up with a curve. It's not a parabola, but it's kind of similar in that it's curvy. And then here, we're going to be curvy on the way down. So this is our function, the cubing function, x cubed. For the domain and the range, we're going to pay attention to our arrows. Notice this is going to the left, down and to the left, and this one is going up and to the right. So that means our domain will be all real numbers. And again, this makes sense because if I give you a real number, you can multiply it by itself multiple times and you can get some number cubed. Similarly, if I look at the arrows, it goes down forever and up forever. So its range is also going to be all real numbers. Now, this is different from the squaring function because when you multiply a negative number an odd number of times, you end up with a negative. If you multiply an even number of times, if you multiply a negative number an even number of times, you're going to get a positive. So when we had the squaring function, the negatives always would cancel out and we would only get positive y values. For the cubing function, you're always left over with one extra negative. So you're always going to end up with a negative value if you're cubing a negative. So that's our cubing function. Now we're going to do some different functions. So we could do x to the fourth and x to the fifth and x to the sixth, and that would be going on forever. So we're going to stop here with cubing. Another reason we're going to stop with cubing is because, like we mentioned before, if I were to transform a squaring function, if I were to shift it, stretch it, or reflect it, I would get any type of quadratic. It's not quite the case with the cubing function. So with the cubing function, if we had like x cubed plus x minus 3 or different types of cubing functions, we could get something that didn't look like this little shimmy. And we'll be talking about that in our second unit when we discuss polynomial functions. But what we're going to know for right now, what's important for us right now, is that the cubing function is going to go up on the right and down on the left, and it has this little shimmy in the middle. So we want to keep that tucked away in the back of our minds so that when we get to polynomial functions, we have something to compare it to. All right, so now that we've got some power functions, x, x squared, x cubed, let's look at some funkier types of functions. You ready? Alrighty, up next, we have the reciprocal function. So the reciprocal function is going to take any number as its input and find its reciprocal. Again, clever naming, right? So the reciprocal of a value is just going to flip it. And there are two ways that we can express this using notation. So we could say that f of x is going to be 1 over x. So this is the most common way of indicating reciprocal. You take the value and you flip it. So a number over 1, if I flip it, becomes 1 over the number. Another way to represent this would be to say f of x is x to the negative 1 power. So remember that if we have a negative exponent, that's going to find the reciprocal of the value. So the reciprocal function could also be expressed using a negative exponent. My personal preferred tendency is to use this fraction notation unless I'm working in conjunction with lots of other exponents. When I think about the different types of numbers I can take a reciprocal of, there's one number where it breaks, and that's 0. We can't have 1 over 0 because we can't divide by 0. So when I go to find some points for my graph, I can't start out with 0 because 1 over 0 is undefined, it doesn't exist. So I'm going to start out with 1. 1 over 1 is 1. 1 over 2 is a half. 1 over 3 is a third, so it's about a third. And so on. So as I keep increasing the denominator, a quarter, a fifth, a tenth, a 1/1,000,000th, I'm going to get smaller and smaller and smaller values. I'm never going to cross this threshold of 0 because 1 over any number is going to be some, well, 1 over any positive number is going to be some really small positive value. What that means is we're going to end up having a horizontal asymptote of the x-axis. So I'm going to indicate that by putting a dotted line over the x-axis. We'll talk about asymptotes in more detail as we talk about properties of functions, but what we need to know right now is an asymptote is a value that a function approaches. It may or may not reach it. Okay? So in this case, we are approaching 0 from the top here. But I still need to know what's going on here between 0 and 1, right? So let's pick some other values to graph. If I graph a half, if x is a half, the reciprocal of a half is 2 over 1, which is 2. If I pick a half of a half, which is a quarter, the reciprocal of 1/4 is 4 over 1. So that's going to bring me up to 4. So we have kind of a similar thing happening here as we get closer from 1 to 0 with this function. It's going to start becoming very, very, very large. Again, I can't input 0, but as my numbers, as my inputs get smaller and smaller, 1/10th, 1,000th, 1,000,000th, then my y values are going to get bigger, 10, 1,000, 1,000,000. So we end up also with a vertical asymptote along the y-axis here. And if I connect these points, kind of have this turning happening at 1. When we get closer to each of the axes as we move to the right or as we get closer to 0. Now, a similar thing is going to happen with the negatives. So if I take -1 and I find its reciprocal, I get -1 back. The reciprocal of -2 is -1/2. And the reciprocal of -3 is -1/3. Kind of approximately there. So we're going to get the same sort of horizontal asymptote happening there. And as I move from 1 over to 0, we're going to get a similar vertical asymptote happening. So as I, let's pick -1/2, that's going to bring me to -2. And -1/3 is going to bring me to -3, and so on. So we're going to get closer and closer to the y-axis in that way. So this is our reciprocal function, very different from those polynomial functions we looked at, right? This is very different from a line or a parabola or a little shimmy. So we've got some strangeness happening with these asymptotes. So that, of course, is going to impact our domain. We can express our domain in two ways. Again, we can use either interval notation or set builder notation. So I'm going to show you interval notation first for this one, but my preferred notation for this particular function is using set builder. It's just easier for me to write. But if you prefer interval, if that's easier for you, by all means. So on my giant metal sheet, and I'm moving from left to right. So I notice this arrow here is pointing to the left forever. So I start out at -infinity. And I have this arrow pointing to the right. So I go off to +infinity. But I can't just stop there. That's why I left a little bit of space. I probably should have left more space, actually. We'll find out. So I left some space because of this asymptote, right? We have this tricky situation where we can't divide by 0. So this function starts out at -infinity, and it can get infinitely close to 0, but it can't get to 0. So we kind of have this break happening. So to indicate that break, I'm going to have 0, and then I'm going to use a parentheses. And then I can put a 0 here with a parentheses. So I start out -infinity, and I go all the way up to, but not including 0. And then I pick up right after 0, infinitesimally close to 0, but not 0, and move off to infinity. And then to indicate that I'm joining these two, I'm going to use what's called the union sign. Just looks like a U without the tail. So this is saying from -infinity to 0, union 0 to infinity. You can think of the union as like saying, and also, or kind of gluing these two intervals together. Now, as I mentioned, my preferred notation, personally, my personal preference is to use set builder. So I'm going to start out with the set of all x, so that, and in this case, x can be any real number that we want it to be, except for 0. That's the only number we can't divide by. So we're allowed to have any value for x as long as it does not equal 0. Now, the reason I personally prefer this notation better is because if you have a lot of asymptotes or holes, a lot of places where something funky is happening, it's easier just to list out where that break is occurring than it is to union a bunch of intervals together. So in this case, we only have one vertical asymptote. We only have one place where it breaks. So these notations are pretty similar in terms of length, I guess, that it takes to write: pencil, lead, marker, ink. But as we move into more and more funkier looking functions, this notation is going to generalize better. It's going to be a little bit easier to use. Then we'll do a similar thing for the range. If I'm looking at the range, we have pretty much the same thing happening. My metal sheet passes from the bottom to the top. So we have here at -infinity, all the way up to, but not including 0. And then we go up to infinity. So we're having this break at 0 happening again. So we could use set builder notation, all values of y, so that y is non-zero. Or we can use interval notation. We start at a -infinity, go up to, but don't include 0. And then we pick up just after 0 and go off to infinity. So there we have it. That's our first kind of weird looking function. This is going, excuse me. This is going to serve as a kind of foundation for rational functions. So we looked at like x squared and x cubed, and I said x squared kind of generalizes to other polynomials, but x cubed is a little bit funky. Not all of them have the shimmy. So similarly, most rational functions, basically fractions of polynomials, this serves as a good foundation, but they can look very weird. So you should expect things like asymptotes to happen with rational functions. But we could get some other weird things happening. We could have asymptotes that aren't vertical or horizontal lines. We could get holes. So maybe there's just, instead of a dotted line, there's just like an empty spot where the function doesn't work. And that, again, we're going to explore in a lot more detail in our second unit. But just so we have it tucked in the back of our brains, weird things can happen, asymptotes especially, when you have a fraction of polynomials. All right, so now that we've got some polynomial functions down and at least one rational expression, let's look at something a little bit more radical. All righty, so let's give a go for the square root function. See, it's radical. It's got a square root radical. So the square root function does what it says it does. It takes a value of x and it square roots it. So this is basically more or less undoing the squaring function, although it doesn't undo it perfectly. We'll talk about that in a few videos. So for the square root function, you give me an input and I'm going to find its square root. So if you give me 0, the square root of 0 is 0. If you give me 1, the square root of 1 is 1. If you give me 2, the square root of 2 is a mess, so I'm not going to graph it yet. Similarly, the square root of 3 is a mess, so I'm going to move on to the next perfect square, which is 4. The square root of 4 is 2. After 4, the next perfect square is 9. So you can see my x-axis went out a little bit further. So I'm going to go over to 9, and the square root of 9 is 3. And now I have enough points that I can connect them. I'm going to move this one just a little bit because I think it was off. Yeah, more or less. There we go. So we're going to get essentially half of a sideways parabola. Now I would continue to move over to the left, except the square root of a -1 is I. It's a complex number or imaginary number. And this is just a graph on the real plane. So I'm going to have to stop at 0 because we can't square root a negative value and get a real number out of it. So that's actually going to impact our domain, right? For the domain, it looks like we're starting here at 0, and then we can square root any positive real number. So for the domain, I'm going to start out at 0 and go up to infinity. Alternately, if you prefer set builder notation, this is the set of all x, so that x is greater than or equal to 0. If I look at the range, the same thing is happening. When I find the square root, this is the principal square root, so there's no minus sign in front of it. It means find the positive square root. So since we're finding the positive square root, we can't be negative. And I guess I misspoke. It's really the non-negative square root because the square root of 0 is 0. So for the range, we have all y values so that y is greater than or equal to 0. Or if you prefer your interval notation, going from 0 to infinity. So there we go. That's our square root function. Now, you notice when I graphed this function, I picked values of x that were going to be easy to graph. So I picked perfect squares so that I could find nice points to graph rather than having to approximate, the square root of 2 or the square root of 3. So that would be my recommendation to you, is that when you go to graph a function like this, think about where you want your x values and your y values to be, set up your graph space, and pick some good numbers for them. So I'm going to ask you to try this next graph on your own. The next one is going to be the cubed root function. So instead of finding a square root, find a cubed root. So take a moment, pause the video here and work through that. And then when you're done, unpause, and I'm going to have the answer on the board and we can check. When you do this, also make sure you've got your domain and your range set up. So we're going to do the cubed root function, which is just the cubed root instead of the square root of x. So pause here and take a moment to work through that. Alrighty, so how did we do? So my cubed root function is our cubed root function. So f of x is the cubed root of x. So for this one, unlike the square root function, you actually have any input. Because remember when we did the cubing function, if I took a negative number and cubed it, I got a negative number out of it. So that means if I have a negative x value and I find its cubed root, I can get a negative value out of it. So the cubed root of -8 is -2, whereas the cubed root of +8 is a +2. Just like with the cubing function, we have a little shimmy happening. So here around 0, it sort of changes concavity, and we have that little curviness occurring. Because you can cube root any number, our domain is all real numbers, and the range is all real numbers. If you chose to use interval notation for your domain and your range, that's also totally fine. Okay, so we have, let's see, 3, 4, 5 more to go. So we're just over the hump of halfway through this video. So in terms of the functions. So the next 3 common functions that we're going to look at are actually families of functions. What that means is we're going to be looking at essentially like a collection of similar functions. But when we go to graph them and name them, we're going to be looking at a specific example to represent that family. It's more or less like I could have said, let's graph any power function. So that would be x to the n. So in order to graph one of those functions, I have to pick a number for n. So we did x squared and x cubed. So now we're going to look at a few different families of functions. Most likely you've seen many of the functions we've done so far. Most likely you may not have seen most of the functions we're going to be doing moving forward. You might have seen 1 or 2 of them, but they may be new for you. So this next family of functions we're going to look at are exponential functions, and they're of the form a number to the x power. So let's take a moment and look at those. Alrighty, so for our first family of functions, we're going to look at exponential functions. And as I mentioned, these functions are going to look like some number to the xth power. So our variable now is not in the base of the exponential expression, it's in the exponent. That's why it's called an exponential function, because that's where the action's happening. So in general, we're going to look like f of x is equal to a to the x power. So in this case, a is standing in for a number. So in order to graph this and kind of see what's going on, we're going to do an example. So I'm going to do the example of f of x equals 2 to the x. So you could pick something like 3 to the x or 4 to the x if you prefer. Just be forewarned, the larger your base, the larger your vertical axis is going to have to be in order to graph it. So in this case, let's start out by plugging in numbers. Again, we're going to be graphing f of x equals 2 to the x, but this process would be similar for any other value you chose for your base. So 2 to the 0 is 1. Remember, anything other than 0 to the 0 power is 1. So when x is 0, the y value is going to be 1. Next, if the exponent is 1, 2 to the first is 2. So when x is 1, y will be 2. And we're just going to continue. So when the exponent is 2, 2 squared is going to be 4. So you can see why this is going to get a little bit big. Because now when I do 3, 2 cubed is going to be 8. So we're going to go up here. And we're going to increase fairly quickly. So that's why often in like common vernacular, if you're increasing exponentially, it means you're increasing very quickly because the exponential function increases quite fast. So that's what's happening for our positive inputs. Let's see what happens for the negative inputs. So remember when we had our reciprocal function, one way to represent a reciprocal was to use -1. So when you have negative exponents, what that's going to do is it's going to flip the expression. So if I have 2 to the -1, that's going to be 1/2. If I have 2 to the -2, that's going to be 1 over 2 squared, which is 1/4. And if I have 2 to the -3, that's going to be 1 over 2 cubed, which is 1/8. So as we increase our negative values here, the fractions are getting smaller and smaller and smaller. So if I graph this at -1, we're at 1/2. At -2, oh gosh, we're at 1/4. And at -3, we're at 1/8. So the bigger the negative number, the closer we become to 0. We will never reach 0 because 2 to any power is going to be a positive number, right? There's 2 to some power equaling 0. We're never going to get there. So I'm going to kind of indicate that, getting closer and closer here to the x-axis. And then as I move to the right, I go off super quickly and increase in that manner. Now, just like with the reciprocal function, since we're getting close to the horizontal axis, we're approaching 0 but not reaching it. That means we're going to have an asymptote there. So I'm just going to indicate that like so. Now, there are some common features of all exponential functions. So all exponential functions of this form are going to have that horizontal asymptote of the x-axis, and they're all going to go through the point 0, 1, because any number that's not 0 to the 0 power is going to give you 1. And they're all going to have this general shape, although they may increase and then therefore decrease more quickly or more slowly, depending on the value of your base. We'll be exploring exponential functions in a lot more detail in the future. So again, we're going to tuck this one away in the back of our heads, kind of take some time to get used to working with it so that when we get to it in the future, it's not like, oh my gosh, totally strange. It'll be more like, oh, this is easy, it's review, right? When I look at the domain, I can raise 2 to any power I want. That's why we have arrows that point to the left and arrows that point over to the right. So our domain are all real numbers. For the range, 2 to any power is always going to be greater than 0. So we have this horizontal asymptote at 0 here. We approach 0 in the terms of the y values, but we never reach it. So to indicate that we approach it but don't reach it, we're going to use an open parentheses, and then we go off to positive infinity. If you prefer to use step builder notation here, we would have the set of all y, so that y is greater than 0. This time it's not greater than or equal to, because we don't actually equal 0, we just approach 0. Okay, so we saw like the squaring function, and then we saw kind of its opposite, the square root function. So here we have an exponential function. Now we're going to look at its kind of opposite, which is a logarithmic function. So let's clear the board and work through the next example. Alrighty, so for logarithmic functions, and here's our general format. Again, this is a family of functions, so we're going to do one specific example, and then we'll do a deeper dive of these types of functions in the future. So for a logarithmic function, it has the format log with a base of a of x. Now, if you haven't seen logarithms before, that's okay. Like I said, we're going to do a deeper dive later in the semester. What you need to know for this, for purposes of this example, is that the logarithmic function basically undoes the exponential function. So I'm just going to create a quick table based off of what we had before. So before we had x, and then we had 2 to the x, right? This was our example that we had. And then we picked some values of x, both negative and positive. So 2 to the 0 was 1, 2 to the first was 2, 2 squared was 4, go one more, 2 cubed was 8. And then 2 to the negative 1 was 1/2, and 2 to the negative 2 was 1/4. So these were some of the points that we chose to graph for our exponential function 2 to the x. To use this table to graph the logarithmic function, we're basically switching the roles of x and y. So this is now x, and this is now log base 2 of x. What this means is if you see an expression like log base 2 of 1/4, right, if our x value is 1/4, what that means is 2 to what power will give me 1/4. So in this case, 2 to the negative 2 will give me 1/4. So it's doing that exponential function backwards. Like I said, right now, we're just kind of getting an idea of what this function looks like. We're going to talk about logarithmic functions in much greater detail later in the semester. For now, we're going to use these as our x values, and then we'll graph the corresponding y values. So at 1/4, the y value is -2. So here's 1/2, 1/4, so very close here. At 1/2, the y value is -1. At 1, the y value is 0. At 2, the y value is 1. At 4, the y value is 2. And at 8, the y value is 3. All right. So we're getting something that looked kind of like the exponential function, but turned on its side a little bit. It gets really close to the y-axis, but never reaches it. And then it slowly increases as we move to the right. So because it gets closer to the y-axis, but doesn't reach it, it's going to get closer and closer to 0. I'm going to put a vertical asymptote there. All right. Yeah, so this one's a little bit funky, but that's okay. Oh, I should put here for our example that we're using f of x equals log base 2 of x. So just like we used x and then 2 to the x to help us graph log base 2, you could do that for any value. So if you needed to graph log base 3 of x, I'd recommend first creating just a table using these inputs for 3 to the x, and then you switch your x's and your y's. That's the easiest way to graph it that I know of. So for our domain, because of this asymptote here, we're going to start out at 0 and go off to infinity because we have this arrow. For the range, notice this arrow goes down forever, so we can have any large negative number we like. So we have negative infinity. And then we have this arrow that is slowly going upwards, so we have positive infinity. Okay, we've got one more family of functions to look at, and then we have two more specific functions. So this next family of functions, I think you'll find a lot easier than logarithmic functions. So let's take a look at it. Our third and final family for today are the constant functions. Constant functions are functions that are kind of like super stubborn. No matter what x value you give them, they will always give you the same answer. So kind of like a kid asking, their parents for something, and the parents always say no, or always say yes, I don't know. So in the case of a constant function, if I tell you 7, you're going to spit out some answer, maybe 15. So then if I gave you -2, you would also spit out 15. Or if I gave you π½ you would spit out 15. So a constant function is always going to give you the same answer no matter what. So to express this generically, we're going to say f of x equals c. So in this case, c is that number that it's spitting out. So as with our other family type functions, we're going to have to use an example here. So I'm going to use the example of f of x equals 2. So in this case, no matter what number you give me, I'm going to spit out 2. So if x is 0, my y value is 2. If x is 1, my y value is 2. If x is 2, my y value is 2. If x is 3, my y value is 2. Right? And so on forever that way. And same thing with negatives. If x is -1, my y value is 2. If x is -2, my y value is 2. If x is -3, my y value is 2. Right? So in this case, because my constant value is 2, all of those y values are just going to stay 2. So when you graph it, you end up getting a horizontal line. So all constant functions are going to be horizontal lines at the value that you pick. For the domain, you can give me any number you want. I'm just going to spit out the same answer each time, but you can give me any real number. There's no problem there. So our domain is from -infinity to infinity. For the range, for this particular example, we have a particular range. The only possible answer I could have given you here was 2. So our range is going to be the set containing 2. Now, this is a different kind of notation that we haven't used yet in this video. This is in list form. So list form is where you use these braces or curly brackets and you list out the possible answers you can get. So in this case, the only possible answer I can get is a 2, so I've got to use 2. We don't want to use parentheses, we don't want to use square brackets, because parentheses or those square brackets are reserved exclusively for interval notation. So when we're using a list, we want to make sure we're using these braces for our answer. Now, this is our range for our specific example, but if I had chosen the function f of x equals 1, then all of my y values would have been at 1 instead of at 2. So for f of x equals c, then the range is going to be the set that includes c. So I want to pause here for a second and talk about the difference between in general and specific cases. So our specific case, our answer here was a 2. The general case, think of it kind of like a formula. So the general case is going to be c. That doesn't mean if I give you a specific constant function, your answer is c. It means if I give you a specific constant function, your answer is whatever the constant is. So as a real quick side example here, if I were to say, what is the range of f of x equals -21, you would identify this as a constant function because we have f of x equaling a constant value. In this case, -21 is playing the role of c. So for the range, you would have negative 21 as the range of that function. So since negative 21 is playing the role of C, it gets to play the role of C in the range as well. All right, so that's it for our family of functions. We have 2 more functions to go through. So let's zip through those and then we'll be done with our first video here. Our penultimate function to graph is the absolute value function. So the absolute value function very cleverly finds the absolute value of a number. So for our equation, we're going to use the absolute value bars. So f of x is equal to the absolute value of x. Remember that the absolute value is a way of just removing the sign of a number. So it takes any number and turns it into a non-signed number or a non-negative number. So if I find the absolute value of 0, which is always humorous, because that's the absolute value of 0, lol, you end up with 0. If I find the absolute value of 1, I'm going to get 1. The absolute value of 2 is 2. All the positives are boring here. The absolute value of 3 is 3. In fact, if I give you any positive value and then you take its absolute value, you get the same thing. So no matter what I give you, as long as it's positive, you're just going to spit out the same thing. Doesn't that sound like something we did earlier, where if I gave you something, you just spit out the same thing, like you maintained an identity kind of? So for values that are greater than 0, the absolute value function is going to look like the identity function because it's going to just maintain that value. However, for numbers that are smaller than 0, so negative numbers, now we have a bit of a change because the absolute value of, say, -1 is a positive 1. The absolute value of a -2 is a positive 2. The absolute value of -3 is positive 3, and so on. So if you give me a negative input and I find its absolute value, I'm going to get the positive form of it. So we end up with something like that. So the absolute value function, when we graph it, looks like this V. For the domain and the range, there's no limits on what I can give you for the domain, right? This arrow goes all the way to the left and this arrow goes to the right, and there are no asymptotes or weird things happening in between. So the domain of this function is all real numbers. For the range of the function, the absolute value always spits out a non-signed number. In other words, it's going to spit out a non-negative value. So for the range, there's nothing below the x-axis. We start out here at 0, and then we can continue up forever. Doesn't matter that it's up forever on both sides, we just need one to make it work forever. So for the range, we start at 0, and we go off to infinity. Because we can include 0, we're going to make sure we use the square bracket. So there we go. That's our absolute value function. All right, let's look at our very last function, which is called the greatest integer function. It's a little bit weird, that one. So the greatest integer function is a great example of something called a step function. It's used often in computer programming if you're trying to basically take any input and turn it into an integer. So this is a way to take any decimal and transform it into an integer. The equation for the greatest integer function is not going to be really helpful to us. So there are 2 notations that are fairly common notations that we'll use. So the first one looks like that blackboard bold. So it's kind of a bold square bracket with an X in the middle. Or what you might see more often in programming languages will be int of X. So int of X is going to represent our greatest integer function. So that's the notation, but it's not helpful if I say, evaluate this function. We don't know what that means. So I'm going to write like the formal definition of the greatest integer function down at the bottom here. But the formal definition is, I'll use this notation. The greatest integer of X is the greatest integer not larger than x. In other words, we want the biggest integer that's not going to exceed the value I give you. So if I gave you 2.3, the biggest integer, the biggest whole number that's not larger than 2.3 is 2. So if I were to find, out of space here, so if I were to find the greatest integer of 2.3, that's going to give me 2. If I were to find the greatest integer of 2.9, the largest integer that is not greater than 2.9 is also 2. So notice this is not a closest integer function. 3 is an integer that's closer to 2.9 than 2 is, but 3 is larger than 2.9. So you can kind of think of the greatest integer function like a rounding down function. For positives. Okay, we'll get to negatives in a moment. Before we do the graph, however, let's talk about the domain and range. The purpose of this function is to take any real number and turn it into an integer. So just like the fancy bold R stands for real numbers, Z, fancy Z, stands for integer. Why Z for integer? It has something to do, I think German is the root of it. So there's a value for amount or number or something in German that begins with Z. I don't speak German, so I don't know what it is. If it bothers you, you can remember that it's a drunk I, so it's kind of sliding. So the symbol for integer is a drunk I or a Z. So our goal is to take any real number and turn it into an integer. So if I give you 2, so if I were to give you the greatest integer of 2, the largest integer that is not bigger than 2 is 2, right? 2 is not bigger than 2, and it's the closest integer to itself. So that means if I go to graph, the greatest integer of function of 2 is going to be 2. And then as we saw, 2.3 was also 2. 2.9 was also 2. Any number that's between 2 and 3 is going to round down to 2. And then once I get to 3, it's going to jump up to 3. So the way that we're going to represent this graphically is I'm going to plot an open circle at 3, 2. And I'm going to connect those with a horizontal line. So that means no matter what input you give me between 2 and 3, so maybe 2.8, the y value is still 2. I'm putting this open circle here because once I get to 3, now I'm going to go up to 3. And then when I get to 4, so 4 is out here, I'm going to stop and I'm going to skip up to 4 and so on. So this function is going to look like a bunch of these little horizontal lines with a filled in point on the left and an open circle on the right. So I'm going to continue this pattern moving down towards the left. So here we're going to have an open circle at 2, 1, a closed circle at 1, 1. And we'll check. That means everything between 1 and 2 is going to round to 1. Everything between 0 and 1 is going to round to 0. And we're just going to continue with this pattern. Now, there's no real easy way to indicate that this is happening forever in both directions. So we're just going to fill up the whole graphing space to show that we can't graph anymore in this case. But it is continuing in this manner up and down forever and left and right forever. Now, the reason why I kind of like winced at round down is because when you get to the negative numbers, it's still true, but it feels wrong. So for instance, if I wanted to know what's the greatest integer of -2.5, If I think in terms of rounding down, I might be persuaded to say -2. But if I look at what's happening at -2.5, we're at -3. So let's think about why. If I compare this to -2 and -3, with negative numbers, your greater than less than get reversed, remember? So -2 is greater than -2.5. So I want the greatest integer not larger than the number I've been given. So the greatest integer that's not larger than -2.5 is actually -3. So this is why just thinking round down can be a little bit misleading. It's great for the positives. And if you get the positives and follow the pattern, then you'll be okay. But if you just have a negative number, it can be a little bit confusing. All right, good news. That concludes this first video. It feels like it was a bit long, so hopefully you can pause. Maybe I'll see if I can figure out chapters on YouTube, or at least put some timestamps someplace so that if you need to review a particular function, hopefully I'll be able to do that. And in our next sequence of videos, we're going to be manipulating these basic functions as well as some other random functions that I might be giving you. So we'll be transforming them. So we'll be taking one of these common functions, let's say the absolute value function, and then I'll say, okay, let's stretch that function horizontally and then shift it up by 3 spaces. So in order to do those transformations, in order to change that function, we need to know what that basic common function looks like. So make sure that you are familiar primarily with the name and the equation and the graph, right? So that you have those things connected. If you have those, then you can figure out the domain and the range from that. So if you're kind of short on memorization space, like me, I have a tough time memorizing stuff. So as long as I remember the equation and the graph, and most of our names match our equations. So as long as I remember the equation and the graph, then I can kind of derive or figure out the other stuff. So that's where we're going to stop for this video. Hopefully it was helpful in helping you figure out some of the common functions, and I look forward to seeing you in the next one. Bye for now.